So first of all, thanks for organizing this conference, and thank you for inviting me. So, so we're here to talk about outline of a theory of truth. There are a lot of, this paper covers a lot of ground, as you all know. So one of the contributions of this paper, we get some criticisms of Tarski's approach, which Kripke calls the orthodox approach. We also get a characterization of the ungrounded sentences, and characterization which brings this notion to the fore of the truth literature. So the liar sentence, this sentence is false. This is characterized as ungrounded, but not just the liar. So the truth teller, we're also told, is ungrounded, right? So this sentence is true. So Kripke says not paradoxical, although it shares some of the same strangeness as the liar sentence. And if you were told that this sentence was true, or if you were told that the sentence was false, it might seem arbitrary either way. Okay, so what are the criticisms of Tarski's approach? So one of the criticisms is that it seems to be overly restrictive, right? So there are certain scenarios that Kripke describes where there's a relatively straightforward, intuitive assignment of truth values to all the statements, but we don't seem to be able to accommodate it within the orthodox framework. So this is one criticism. It's just too restrictive. Now, despite the fact that it's too restrictive, there's something else that Kripke says about it, which is pretty interesting. So Kripke writes, one surprise to me was the fact that the orthodox approach by no means obviously guarantees groundedness. So despite the fact that this orthodox approach is too restrictive, it seems that perhaps ungrounded sentences also appear. They appear within these classical languages, this hierarchy of classical languages. Now, at the time, Kripke presented two potential sources of ungroundedness within Tarski's framework, within the orthodox framework. And he writes that he did not know even quite how to state the problem. Some substantial technical questions in this area are yet to be addressed. So he raises these two puzzles. Are these instances of ungroundedness within Tarski's framework? And then he says he doesn't know how to address it. So now, 50 years later, I think we can say much more about these examples. The irony is that you can solve these questions, you can demystify these examples using Kripke's own work on other topics. So Kripke did a lot of work on the second incompleteness theorem. Some of the ideas that he came up with in that area are useful here for demystifying these examples. So I'm going to discuss that work, and then I'm going to use these examples as a starting point to discuss just some very surprising connections between the incompleteness theorems and well-foundedness. So this is a line of research that emerges from Kripke's work on this topic, emerges from the outline of the theory of truth. Okay, so that was the introduction, of course. Next, I'm going to introduce the two puzzles. Then I'm going to describe Kripke's work on incompleteness. Then I'll present the solutions to the puzzles. And finally, I'm going to come to the longest section where I describe generally what is this connection between incompleteness and well-foundedness that Kripke put his finger on. Okay. The two puzzles. Well, to introduce the two puzzles, I'm going to need to say a few technical things, introduce some definitions. So we're going to be talking about the language of arithmetic. The language of arithmetic, for our purposes, we'll say has 0, 1, plus, times, and less than. We say that an existential quantifier is bounded if it's immediately preceded by a bound. For some x less than t, and f of x. There's some technical restrictions. X can't appear free in t, and so on and so on. But the point is, you're not saying that some number has a property. You're only saying some number up to some bound. Below some bound has a property. Universal quantifier is bounded. Same thing except with a conditional. For all x, if x is less than t, then f of x holds. We use the notion of a bounded quantifier to define complexity classes for formulas in the language of arithmetic. So a formula is called sigma 0, also called pi 0, if all of the quantifiers in it are bounded, so no unbounded quantification in these formulas. And then we can use this to define an entire hierarchy. sigma n plus 1, these are the formulas that have the form for some x, f of x, where f of x is pi n. Pi n plus 1, these are the formulas of the form for all x, f of x, where f of x is sigma n. So roughly, a sigma 1 formula, there exists an x such that, and then some bounded thing. Pi 2 is for every x, there is a y such that some bounded thing. And it just percolates up like that. So sigma n is n quantifier alternation starting with an existential. Pi n is n quantifier alternation starting with a universal. But with that out of the way, let's talk about the puzzles. So the first puzzle, here's Kripke, an outline of a theory of truth. The concept of truth for sigma 1 arithmetical statements is itself sigma 1. And this fact can be used to construct statements of the form of the truth teller. So what's going on here? There is a truth predicate in the language of arithmetic for the sigma 1 sentences. And it itself is a sigma 1 formula. So the self-reference lemma or fixed point lemma guarantees the following fact. There is a sigma 1 sentence, tau, that is equivalent to the claim that tau is a sigma 1 truth. And Kripke is asking, what's the status of this statement? Is it true or false? Either way, it seems like it would be kind of arbitrary. It's hard to see what could point the needle in either direction. Okay, on the other hand, right, whatever this statement is, it's a statement in the language of arithmetic. We're just talking about the language of arithmetic, no truth predicate in it. So this is merely a statement which ascribes a sigma 1 arithmetical property to some number. And it does seem hard to swallow that it would be totally arbitrary. It seems like this must be somehow disanalogous from the truth teller sentence. Okay, so there's something mystifying about this example. There's something genuinely puzzling here. The second puzzle. So Kripke writes, standard theorems easily allow us to construct a descending chain of first-order languages, L0, L1, L2, and so on, such that for each I, Li contains a truth predicate for Li plus 1. And he says, perhaps, but he doesn't know. I don't know whether such a chain can engender ungrounded sentences. Okay, so what is he talking about here? So this is, he says standard theorem. So there's a standard trick here that he's alluding to that was developed by Harrison. So let me explain how the trick is supposed to go. For any set of natural numbers, or any set A of natural numbers, you can expand the language of arithmetic with a predicate. We'll call it A of X, which just applies to the things in the set A. So you can expand the language of arithmetic with a new predicate that picks out that set for any set. Call that language LA. So LA is the language of arithmetic, but with a predicate for A. True LA, let's say, is the set of truths in the language LA. Right, so if you interpret the language of arithmetic as just being about the natural numbers, and this predicate A is interpreted as picking out A, true LA is the set of truths of the language LA. It's a truth predicate for the language LA. What that means is L sub true LA, that's the language of arithmetic expanded with a single predicate, and that single predicate is a truth predicate for the language LA. So L sub true LA is the language of arithmetic plus a truth predicate for LA. Does that make sense? Okay. The Tarski jump is just the function which takes in a language LA and outputs the language L true LA. So it's the function which takes in a language and produces the language which just has a truth predicate for that language. Now, the Harrison linear order. The Harrison linear order is one of the central objects of study in recursion theory. It's a linear order. It's a computable linear order. It's ill-founded. So this linear order, the Harrison linear order, has infinite descending sequences inside of it. However, you can still iterate certain functions along this linear order as though it were well-founded. With a well-founded linear order, you can iterate a function along that order. You can do that with the Harrison linear order for certain functions. And that means you can iterate, in particular, in this case, you can iterate the Tarski jump along this order. So you start iterating the Tarski jump along this order, When you're iterating the Tarski jump along the ill-founded part of the order, you get a descending sequence of languages. So in particular, you have a language L0, which is just the language of arithmetic with a truth predicate for L1. And L1 is just the language of arithmetic with a truth predicate for L2, and so on, all the way down. So Kripke's asking, does this yield ungrounded sentences? I mean, this top language has truth predicates for all of these, all the things beneath it. Can you formulate like a sort of, Yablo truth teller type sentence in that language that just it never bottoms out? It just keeps going all the way down the hierarchy, this inverted hierarchy? That's what Kripke's asking. Okay, so those are the puzzles. Can we get ungrounded sentences in either of these cases? And this is all within the classical framework, the classical orthodox framework. So let's talk about Kripke's work on the incompleteness theorems. So Kripke returned many times in his career to proofs of the second incompleteness theorem. This was a subject that he was very interested in. He wrote a bunch about this. Gödel's original proof, Gödel's proof of the second incompleteness theorem, as we all know, is very strange. Right? It's a very unusual argument. In Gödel's paper, he says the analogy of the result with Richard's antinomy jumps out, and there's also a close relationship with the liar, right? Because Gödel, in his original proof, he constructs this self-referential sentence. So Kripke said at various points, this is an ingenious argument. However, there should be a different way of proving this. There should be a way that feels a little bit more standard. So Kripke repeatedly emphasized that instead of using self-reference, we should be able to prove Gödel's theorem using minimalization. This is the term he used, minimalization. What's the basic idea here? The basic idea comes out of another incompleteness theorem due to Kuratowski, which predates Gödel's. So already when Gödel proved this, there were other incompleteness theorems on the scene that were somewhat less general. So here's the theorem that Kripke always discussed, attributes to Kuratowski. Assume that there is a strongly inaccessible cardinal, then ZFC does not prove that there is a strongly inaccessible cardinal. So this is a kind of incompleteness theorem. Right? There's something that ZFC isn't proving under this hypothesis. How would you argue for this? There are a lot of ways of arguing for this, but here's one. Okay, so let's do it. Let's assume that there's a strongly inaccessible cardinal. If there's a strongly inaccessible cardinal, there's a least one, right? Because cardinals are well ordered. So let kappa be the least strongly inaccessible cardinal. Now cut the universe off at kappa. It follows from the definition of strongly inaccessible that V kappa is a model of ZFC. So we have this model of ZFC, V kappa. There are no strongly inaccessible cardinals inside V kappa, because kappa was the least one. So V kappa is a model of the theory, ZFC plus the statement, there are no strongly inaccessible cardinals. And if we have a model of ZFC plus there are no strongly inaccessible cardinals, that means ZFC doesn't prove the existence of a strongly inaccessible cardinal. This is an incompleteness theorem with a totally transparent proof. Now you're just using, right, like the least number principle, right, in the form of taking the least strongly inaccessible cardinal, and then you get a counter model. This is the way you would expect incompleteness theorems to go if you had never seen Gödel's proof. So Kripke asked, can we do this for Gödel's second incompleteness theorem? And Kripke produced a bunch of interesting proofs along these lines. There's a famous proof that he gave using the notion of a fulfillable sequence, which maybe some of you know, for a weak form of Gödel's theorem, so slightly weaker. And this weak form is that no sufficiently strong pi2 sound theory proves its own pi2 soundness. Pi2 soundness is a stronger notion than consistency, stronger but related. So this is like a slightly weaker form of Gödel's theorem. But Kripke had a proof that uses this minimalization. And it's a totally semantic argument. Kripke later turned this into an interesting novel refutation of the Hilbert program. Kripke gave this kind of argument that the Hilbert program was, in some sense, self-refuting. I'm going to describe this in a second. In this argument, Kuratowski's idea is still there. So this time, what we do is we attach code numbers, Gödel numbers, to proofs, and we're going to apply the least number principle again. I mean, this time, least number principle for natural numbers, not for ordinals. So the Kuratowski idea is still there. So what is Kripke's argument that the Hilbert program is self-refuting? This is going to be important for what happens later. So according to Kripke's reconstruction, Hilbert had a particular goal, and the goal was to prove this statement. For any proof P of a pi 2 statement, for all x there is a y phi xy, and for any m, there's a proof Q of some instance, phi mn. So the thought is, if you can prove a pi 2 statement, and you take some number as the value for the universal variable, well, you want to know that the pi 2 statement was true. So there's some witness, phi mn. And moreover, that's delta 0, so it should be provable. So this was Hilbert's goal. For any proof of a pi 2 statement and any choice of the universal variable, you should be able to back it up. And Kripke says this has a self-refuting nature, which apparently escaped everyone. So the first thing to note about this is a pi 2 statement itself. For every proof and every m, there is a proof. It's a pi 2 statement about all pi 2 statements. So it has some kind of, impredicative nature, some kind of self-reflexive nature. Kripke writes, we're saying that every pi 2 statement has a certain property. The statement itself is a pi 2 statement. But then he says we have to allow for the possibility that the Hilbertians might have realized the reflexiveness of this statement while thinking of it as merely analogous to a Cretan saying all Cretans tell the truth. So Kripke says, yeah, it's kind of self-referential, but it's not liar-like, it's truth-teller-like. Maybe they noticed that and they thought we can get away with it because truth-teller is not paradoxical. Nevertheless, Kripke shows that there's a problem. Okay, so throughout this talk, I'm going to have to talk about some proofs. That's just the nature of this talk. I don't have time to give full proofs. I'm going to gesture at some ideas, try to give you an impressionistic sense of what's going on in some of these proofs. If you have questions, I'm happy to talk about the details of these proofs in Q&A or over lunch, whatever you want. The basic idea for why this sentence could not be provable is this. If this pi 2 statement is provable, then there is a least proof. Okay? Now, there is a property of coding, which is called coding monotonicity. And that basically means that if you have a proof which talks about some things, the code of the proof has to be greater than the things that are talked about in the proof. That's called coding monotonicity. So you suppose that this pi 2 sentence is provable, then there's a least proof. You then apply coding monotonicity. Given the kind of self-reflexive nature of this sentence combined with coding monotonicity, that means you can find a smaller proof than the least proof, which is a contradiction. Does that make sense? So you take the least proof, but within the proof is talking about proofs of that sentence, so you can find a smaller proof. The basic idea. So Kripke says there's this kind of indigenous, forget the Gödel proof, this sentence is not provable. There's a kind of indigenous failure of the Hilbert program right there. Okay, so this is some of Kripke's work on the incompleteness theorems. Now let's turn to the puzzles from Outline of a Theory of Truth. Puzzle number 1. The self-reference lemma delivers a sigma 1 sentence tau, such that, let's say, provably in PA, tau holds if and only if tau is a sigma 1 truth, right? So this is the sentence which we always think of as saying, I'm a sigma 1 truth. The first thing to observe about this is that there's something actually completely unspectacular about this application of the fixed point lemma. This is a truth predicate. And the fixed point lemma is delivering an instance of the T schema. That means tau is completely unremarkable. For every sigma 1 sentence, you can prove phi if and only if phi is a sigma 1 truth. Does that make sense? This is just the fixed point lemma, self-reference, is just giving you an instance of the T schema. So there are true sentences that have this property. There are false sentences that have this property, right? Independent ones, provable ones, refutable ones. So to make the problem interesting, we have to restrict our attention a little bit. Let's say that a sigma 1 truth teller is a sentence tau, such that tau is literally the sentence, which says the code of tau is a sigma 1 truth. So these are sometimes called literal truth. Yeah, literally self-referential sentences or something like this. To make sure that there are such sentences, you may have to change the formalism a little bit. So sometimes people enrich the language to make sure that these kinds of sentences exist. But okay, we can work in a setup where you can get a sentence like this, a sentence which is literally saying that it is a sigma 1 truth. So it's a theorem in this paper of Halbach and Visser, and I think McGee may have also observed this. The sigma 1 truth tellers are false. And when I say sigma 1 truth tellers, I mean these literally self-referential ones. How do they prove this? Yes, yeah. Yes. Well, you can get this as well if you put like all primitive recursive functions or something like that in the signature.
No, I just wonder, is it actually quantitatively provable that you get it, or is?
I just mean inequality, right? So
Yeah.
I mean it will be provable in PA, but I just mean you have a sentence which is of this form, and the number here is literally the
Yeah, so it's
Gödel number of sentences.
about terms, but then for sigma 1 stuff.
Yeah. So how do you prove that this is false? If a sigma 1 truth teller is true, you take a least witness and you appeal to coding monotonicity again. And you find a smaller witness. Now, I know that this may sound a little bit mystifying, but with sigma 1 truth predicate, if you expand it out, it says there is a sequence that witnesses the truth of the matrix of formula such and such and such. So it mentions these things in there. The things that are mentioned have to be smaller than the witness. So if it sounds familiar, it's almost exactly the same proof. I mean, I wrote slides up where I actually go through the proofs. I mean, it's almost exactly the same. It's the same trick. So you can use the exact same trick to resolve this problem as Kripke used to give this refutation of Hilbert's program. Then in this paper, they say actually the sigma n truth tellers are all false and the pi n truth tellers are all true. Okay. So just that's an aside. So there is a way of seeing what the truth value is of these sentences that at first glance appear like they would be arbitrary if they went either direction. What about the second puzzle? So we have a sequence of languages, L0, L1, L2, and so on, such that for each n, Ln contains a truth predicate for Ln plus 1. Okay, can you get a kind of, truth tellery Diablo sequence? Kripke eventually noted no. The existence of this descending sequence of languages is apparently insufficient for generating ungrounded sentences. And Kripke's reasoning was this. So this is in a paper that was published much later. Well, okay, so the crucial thing here is to invoke Diablo's paradox. So just remind you what Diablo's paradox is. We have an infinite sequence, lambda 0, lambda 1, lambda 2, and so on, such that for each n, lambda n says for all x greater than n, lambda x is not true. And you can get a contradiction out of this, the same way you can get a contradiction out of the liar sentence. So this is Diablo's paradox. So Kripke says, can the result, that is the result that there's a descending sequence of languages, can the result generate any ungrounded sentences? It could, if in the top language L0, we could define an enumeration, RIX, of all the truth predicates of each language. So in this top language, L0, you have a truth predicate for L1, and out of that, you can get a truth predicate for L2, and out of that, you can get a truth predicate for L3, and so on. But you don't have a uniform truth predicate. You don't have a uniform way of talking about truth in the nth language, where n is a variable. If you had that, then you could generate some ungrounded sentences. You could have sentences which say everything after me is true, and it just never terminates. However, if you had that, you could also get Diablo's paradox. So Kripke says, if we had such an enumeration, we would get Diablo's paradox. we could construct an infinite set of sentences, each one of which says that all the following sentences are not true. As Yablo shows, this leads to a contradiction. Therefore, no such enumeration is possible. So this was Kripke's conclusion. Actually, the fact that there's a descending sequence of languages doesn't give you ungroundedness. You need to have a sort of uniformly definable descending sequence of languages. Where does Yablo's paradox come from? So 1993, I think, is the date Yablo published his paper, where he claims the paradox is free of self-reference. This is the thing that he emphasized. Of course, that's a controversial claim, but that was his focus. Many people now call it the Yablo-Visser paradox. So Visser uses a construction very much like this in an earlier paper to resolve actually a version of Kripke's question. So he was interested in this descending sequence of languages. He had a kind of different interpretation of the question. And so Visser used a version of this paradox as well. There's an even earlier version of roughly the same kind of reasoning. In 1975, so this is the same year Outline of Theory of Truth came out, John Steele published a paper where he uses something very similar to this paradox to prove a kind of classic result of recursion theory. Now, I'm not claiming anything about priority or anything like that, or even that Steele had in mind that he was proposing a new paradox, anything like that. You just get the same kinds of methods, okay, showing up in this early paper. Let me say a little bit about this. So remember, LA, that's the language of arithmetic expanded with a predicate for A. The Turing jump of A, so this A prime or A jump, this is the set of sigma 1 truths of the language LA. There are a lot of different definitions of these notions, but this is one way of thinking about it. Set of sigma 1 truths in that language. And we say that A is Turing above B. That's how this less than or equal to T is pronounced. Well, one way of saying it is that you can compute B given A as an oracle. That's a common definition. But another way of thinking about it is that B is both sigma 1 definable from A and pi 1 definable from A. That's another way that this is often stated. Now, A jump, the Turing jump of A, is the canonical set, which is strictly Turing above A. So you can compute A from A jump, but not vice versa. You cannot compute A jump from A. I mean, in particular, you can't, and I mean, another way of saying this, you can't give a pi 1 definition of A jump from A. So the Tarski jump is, something that people have studied. The Turing jump, and I mean, this is one of the central objects in recursion theory. So this is very, very thoroughly studied. And Steele in his paper says, well, there's this trick that Harrison introduced. Using the Harrison linear order, you can produce a sequence, A0, A1, A2, A3, and so on, all the way down, such that for each n, AN is Turing above the jump of AN plus 1. You can take the Turing jump, you can iterate it along this Harrison order, and then you get a descending sequence. So now you get a descending sequence not of languages with each one with a truth predicate for the next, but each one has a partial truth predicate for the next, okay, that you can't get in a simple way out of the lower languages. So Steele was addressing nearly the same question, okay? Roughly this same question that Kripke was interested in, but just phrased in terms of Turing, the Turing degrees, and the Turing jump instead of the Tarski jump. And this is Steele's theorem. So he says, let P be arithmetic. So what this means is that P can be defined using only quantifiers over natural numbers, no quantifiers over sets of natural numbers. We'll come back to that in a second. So he says, there is no sequence, A0, A1, A2, and so on, all the way down, such that one, it's a descending sequence in the Turing jump hierarchy. That's what the first condition says. So for each n, AN is above the Turing jump of AN plus 1. And the second condition says that AN plus 1 is the unique B such that P holds of AN and B. So what is the second condition saying? The second condition saying, roughly, that P is acting like a function. It's acting like a function that is producing a descending sequence. Okay, so if you apply, as it were, P to A0, you get A1. And if you apply to A1, you get A2. And you apply to A2, you get A3 and all the way down. P does not have to be acting like a function elsewhere, okay? But we're just saying with respect to this descending sequence, P is kind of producing the descending sequence. So this arithmetic condition is important here. So what we're saying is there's no simple descending sequence in the Turing jump hierarchy. There's no arithmetic P, which is producing a descending sequence in the Turing jump hierarchy. And if you think of arithmetic as just being a way of measuring simplicity, it's a notion of simplicity, we're saying there's no simple descending sequence in the Turing jump hierarchy. Steele's theorem, I just want to emphasize, so we're getting here a very similar conclusion to Kripke's conclusion after reflecting on the Yablo paradox. There's no simple descending sequence in the Tarski jump hierarchy in the sense that you can't get uniform definitions of what's happening in the top language. And here we're getting there's no simple descending sequence in the Turing jump hierarchy because the sequences can't be arithmetic. So the results are very similar, but also there's a similarity in the proof. If you look at Steele's proof, it's not clear that it's Yablo's paradox. He says at some point, there's something in this argument that is analogous to the second incompleteness theorem. Okay, he says something like that. There's something that's analogous to the self-referential statements that appear in the second incompleteness theorem. And the whole thing the whole thing is described in terms of notions like Turing reducibility and uniform computations and so on. But as many of you know, there's a connection between those recursion theoretic notions and partial truth predicates. If you translate it out into that language, what he's talking about is an infinite sequence of statements, each one of which says everything after me is not sigma 1 true, where each of the statements is both sigma 1 and pi 1. This is the kind of impossibility that he's getting. It's a version of Yablo's paradox. And there are at least some recursion theorists who I've talked to who have said, oh yeah, there's this kind of understanding in the field that that's what's going on in Steele's argument. It's a kind of reduction to this version of the liar paradox with infinitely many sentences, right? They don't even know Yablo's paradox by name, but they know that that's kind of what's happening in this argument. So in 1975, the same year Outline of Theory of Truth is released, you get this early version of the argument that eventually demystifies this second puzzle. Okay. So we've seen the resolution of the two puzzles. As I mentioned, the first puzzle can be diffused using Kripke's own work on incompleteness and well-foundedness, and the second puzzle is defused by deploying Yablo's paradox, an early version of which was used by Steele to very similar effect. So obviously Kripke showed that there was a connection between incompleteness and well-foundedness, right? I mean, he's using this Kuratowski minimalization idea to prove an incompleteness theorem. Steele's result also reveals a connection between incompleteness and well-foundedness. And I'm going to explore this connection in more detail in this section. So let's talk about the language of second-order arithmetic. I noticed that there's an S. That should be missing. Okay. The language of second-order arithmetic, we're going to keep the old symbols, 0, 1, plus, times, less than. We're going to introduce a membership symbol. So we now talk about sets and members. We have two types of variables. So the lowercase letters we think of as variables ranging over natural numbers. And we think of the uppercase letters, capital letters, as variables ranging over sets of natural numbers. So this is the language of second-order arithmetic. A formula is, we're going to call it sigma 1, 0, alternatively pi 1, 0, if it only has number quantifiers in it, no set quantifiers. So these are also called arithmetic formulas. So a formula is called sigma 1, 0, alternatively pi 1, 0, if it has no set quantifiers. And then we get a similar hierarchy to the arithmetical hierarchy. This is called the analytical hierarchy. So sigma 1 n plus 1, these are the formulas that have an existential set quantifier in front of a pi 1n formula. And pi 1n plus 1 is a universal set quantifier in front of a sigma 1n matrix. So again, the lower, the subscript is telling you how many quantifier alternations. This time we're counting the number of set quantifier alternations. And the 1 is telling us we're talking about sets now, not numbers. So there's a hierarchy of formulas we get here. At a few points in these slides, I'm going to mention ACA 0. ACA 0 is a very thoroughly studied system, axiom system. And I noticed also here, this S should also be missing. I don't know why I did that twice. It's a well-studied axiom system in a language of second-order arithmetic. Very thoroughly studied. It's a conservative extension of pan arithmetic. Okay. So that's ACA 0. We recall, Steele proved, as I mentioned, there are no arithmetic descending sequences in the Turing jump hierarchy. Immediately after the proof, Steele writes, we now draw a semantic version of Gödel's second incompleteness theorem for omega logic as a corollary. Okay, so roughly speaking, an omega model is an interpretation of the language of second-order arithmetic where you interpret the arithmetical symbols in the standard way. So you interpret the number quantifiers as genuinely ranging over the natural numbers, and 0, 1 plus times are all interpreted standardly. Membership as well. So the set quantifiers might not range over all sets of natural numbers, but the number quantifiers are restricted to the standard interpretation. So that's an omega model. And here's the Steele's theorem. Let T be an extension of ACA 0 with omega models. Then T has an omega model which encodes no omega models of T. So what does this mean? Let's pause. Before we return to this, think of Gödel's second incompleteness theorem. Gödel's second incompleteness theorem says if you have a sufficiently strong, consistent theory, it doesn't prove its own consistency. Now, as we all know, there's this connection between being consistent and having a model. So let's restate it in those terms. If a theory has a model, it doesn't prove that it has a model. And of course, proving is the same as being true in all models. So let's state it again. If a theory has a model, then there's a model of the theory in which there are no models of the theory. That's a kind of rough gloss on, semantic gloss on Gödel's second incompleteness theorem. Steele is proving this with just omega models. If a theory has omega models, then it has an omega model in which there are no omega models. So how does Steele prove this? This is a Kripke style proof. This is a version of the second incompleteness theorem, which is not proved by coming up with a self-referential statement exactly. What Steele shows is he shows if this were false, you could get an arithmetic descending sequence in the Turing jump hierarchy. Okay, so he says, suppose there's a theory like this. It has a model. Inside that model, there's a model. Inside that model, there's a model, and so on and so on. And he uses this to produce a descending sequence where we know we can't find one. This is exactly the kind of result Kripke was after. So you get this in 1975 in Steele's paper. There are other versions of this. A beta n model, this is an omega model, which is sigma 1n absolute. So what does that mean? So a beta n model is an omega model M, such that for every single sigma 1n sentence F holds in M if and only if F is true. So a beta n model is something such that it's an omega model. Every true sigma 1n sentence is true in it. And every sigma 1n sentence that it says is true is really true. That's a beta n model. So there's a more restrictive notion than omega model. These are special kinds of omega models. Here's the theorem of Mummert and Simpson. Let n be greater than 0. And let T be a theory with beta n models. Then there's a beta n model of T that encodes no beta n models of T. Again, a version of the second incompleteness theorem, right? Except this time stated in terms of beta n models instead of omega models. that make sense? If a theory has beta n models, there's a beta n model in which there are no beta n models. Mummert and Simpson prove this the Gödel way of proving incompleteness theorems. They have a self-referential construction. Kripke asked, in a talk that I saw him give, okay, about the second incompleteness theorem, can you prove this using minimalization? Is there a instead of self-reference, is there a minimalization proof of this theorem? And so in a joint paper with Patrick Lutz, we give a minimalization proof. No self-reference. Okay, we show that if this happened, right, if this were false, you get a descending sequence in a place where we know for independent reasons you can't find descending sequences. Okay. So Kripke emphasized, as I mentioned in the beginning, that versions of the second incompleteness theorem ought to be provable through considerations of well-foundedness. Put self-reference to the side. We should be able to get minimalization, least number principle, well-foundedness proofs of second incompleteness. And we have now seen 4 examples of this. Kuratowski's theorem on inaccessibles, the Kripke refutation of Hilbert program, Steele's theorem about omega models, and this most recent incompleteness theorem for beta n models. So we have 4 incompleteness theorems in some broad sense that are provable without self-reference, just using minimalization. But here things, now here's where things get really strange. There's a converse of sorts that holds. Sometimes you can use the second incompleteness theorem, by which I mean Gödel's theorem, Gödel's original second incompleteness theorem, to prove the well-foundedness of certain partial orders. So occasionally, you have a partial order, and you can show, using Gödel's second incompleteness theorem, that that partial order is well-founded. The earliest example of this that I know is due to Harvey Friedman. So Harvey Friedman gave an alternate proof of Steele's theorem that I mentioned. Steele's theorem is that there are no arithmetic descending sequences in the Turing jump hierarchy. Harvey Friedman gave an alternate proof of that using the second incompleteness theorem. I'm going to give you an example of this in a few slides, but the basic idea is this. He takes the statement of Steele's theorem, okay? He formalizes it. He formalizes the statement of Steele's theorem in a formal language, okay? He adopts the negation of that statement as an axiom, okay? So he works in a formal theory which has as an axiom, it's not the case that Steele's theorem holds. And working within that theory, he proves the consistency of that theory. If that theory proves its own consistency, it's inconsistent. So you infer that Steele's theorem really did hold. It's a remarkable idea. We're going to see an example of it in a moment. One more jump. We did the Tarski jump, the Turing jump. This is the hyper jump, O to the A. So you can think of O to the A as the set of pi 1, truths in the language LA. This is the pi 1, complete set relative to A. If I take 2 sets of natural numbers, A and B, we say that A is hyper below B. That's what that is. If A is both sigma 1 and pi 1 in B. This is one definition. There's another definition in terms of computation, but it means A is sigma 1 definable from B, B is sigma 1 definable from A. That's hyper reducibility. Okay. This is another very thoroughly studied structure in recursion theory. Hyper reducibility and the hyper jump. And the hyper jump is the canonical set. It's like the Turing jump. It's the canonical set, which is strictly hype above A. So you can't give a sigma 1 definition of O of A using A. That's impossible. O of A is pi 1 complete in A. So this is called the hyper jump. So you have this reducibility notion, hyper reducibility, just like Turing reducibility, and you have this associated jump, the hyper jump. Now, what happens if you try to iterate the hyper jump along the Harrison order? It doesn't work. Okay, so you need to deploy certain tricks to be able to iterate a function along the Harrison linear order. You can iterate the Turing jump along the Harrison linear order. You can iterate the Tarski jump along the Harrison linear order. You can't iterate the hyper jump along that order. So here's the question. Is there another source of ill-foundedness? Is there some other way of getting a descending sequence in the hyperjump hierarchy? And the answer is no. Spector did not state this result, although it's an immediate consequence roughly of things that he did state. There is no sequence A0, A1, A2, and so on, such that for each n, an is hyper above the hyperjump of an plus 1. How do you prove this? So here's a proof from a joint paper with Patrick Lutz that I mentioned earlier. To understand this proof, you need to know one fact. ACA0 proves the claim that for every x, the hyperjump of x exists if and only if there is a beta 1 model of ACA0 containing x. If I have a set, constructing its hyperjump is exactly as hard as constructing a beta 1 model that contains that set. That's what this fact is telling us. So ACA0 proves for any x, the hyperjump of that set exists if and only if there is a beta 1 model of ACA0 which contains x. So here's what we do. We want to show that there's no descending sequence in the hyperjump hierarchy. You work in the theory ACA0 plus ds. ds stands for descending sequence, and ds says there is a descending sequence in the hyperjump hierarchy. There is a sequence x for every n. The nth element of the sequence is hyper above the hyperjump of the x at the n plus first element of the sequence. So you work in this theory, ACA0 plus ds. Okay. ds is an existential statement. So if we're assuming ds, that means ds has some witness. Let A be the witness. So A is a sequence. It is a descending sequence. A0 is hyper above the hyperjump of A1. That's what we assumed. That means the hyperjump of A1 exists. Now we deploy the fact. If the hyperjump of A1 exists, there's a beta 1 model of ACA0 that contains A1 inside of it. So far, so good. So we have a beta 1 model. It's a model of ACA0. It has A1 inside of it. But beta 1 models are correct about a lot of things. And from this, you can show not only is A1 in there, A2 is in there, A3 is in there, A4 is in there, and all the way down. So are there hyperjumps? In fact, with a little bit of work, you can show that this is a model of ds. It has all the ingredients right there to construct a descending sequence in the hyperjump hierarchy. So what you've done is you assume there was this descending sequence in the hyperjump hierarchy. You shift down by 1. Take that sequence. You can come up with a model, as it were, where this is a witness to the statement ds. This is a consistency proof. As I just said these things out loud, this is a consistency proof of ACA0 plus ds inside the theory ACA0 plus ds. So this is a technique for using Gödel's second incompleteness theorem to show that a certain structure is well-founded. Why is there a connection between the second incompleteness theorem and well-foundedness? I think at this point it's clear there's some connection. You can prove second incompleteness from well-foundedness and vice versa. What's the connection? What I want to suggest as we wrap up is that actually Gödel's original theorem is very nearly a well-foundedness claim itself. This is not obvious, and as I said, very nearly, right? So it's not even true. It's close to a well-foundedness claim. Let's do the following. So I want you to imagine the consistent, recursively axiomatized extensions of pan-arithmetic as the vertices in a large infinite graph. So we have this large infinite graph. The vertices in this graph are the consistent RE extensions of PA. It's a directed graph. So when do we have an edge between T and U? T points to U if T proves the consistency of U. Okay? So all the consistent RE extensions of PA, and then there's this kind of provable consistency edge relation. Gödel's theorem says the graph is irreflexive. No self-loops. That's what Gödel's theorem says. But if you reflect on it for a moment, you can see this actually shows there's no finite cycles. The edge relation is transitive. If A proves the consistency of B and B proves the consistency of C, A can stitch those consistency proofs together to prove the consistency of C. That means there's no finite cycles. Right? If you had a finite cycle, the original theory would be able to stitch all those consistency proofs together and get a consistency proof of itself, which we know cannot happen. Okay, so there's no reflexive loops. A reflexive loop is a special case of a finite or of a cycle. A cycle is a special case of an infinitely traversable path. So as you start to unwind the incompleteness phenomenon, you might expect that that's the real content of Gödel's theorem. Maybe there are no infinite descending paths in this ordering. That's false. The graph, it turns out, is ill-founded. There are a lot of ways of seeing this. So there are infinite descending sequences of consistent theories, each one of which proves consistency of the next. Just to strengthen the analogy with the other stuff I talked about, one way of showing this is by iterating the consistency operator along the Harrison linear order. Okay, so there's a sense in which this is well defined. We can get a sequence of theories that are all consistent and descending sequence, proving consistency of their neighbors this way. I think this there are a bunch of ways of seeing that this is well-founded. I don't know that this doesn't appear in earlier work. I just know that it appears in our work. So, so Gödel's theorem is not quite a well-foundedness claim, but consistency is just one of a very large family of notions. So we say that a theory is pi1,1 sound if all of its pi1,1 theorems are true. This is a strengthening of the notion of consistency. It's a related notion, right? It's telling you that the theory is correct in some sense. It's reliable with respect to a restricted class of formulas, which is exactly what consistency is saying. RFN pi1,1 of t, this is a sentence in the language of second order arithmetic, which expresses the pi1,1 soundness of t. So it just says you take any pi1,1 sentence and it's provable in t, it's a pi1,1 truth. That's RFN pi1,1 of t. So this is a sentence in second order arithmetic which says t is a pi1,1 sound theory. Okay, here's a theorem from joint work with Fedor Pokomov. There is no sequence t0, t1, t2, and so on, all the way down, of sufficiently strong pi1,1 sound RE theories, such that for each n, Tn proves the pi1,1 soundness of Tn plus 1. There's no sequence of pi1,1 sound theories such that each is proving pi1,1 soundness of the next. So when you shift your perspective, instead of talking about consistency, you talk about pi1,1 soundness, it's actually a well-foundedness theorem. The incompleteness theorem, which says no pi1,1 sound theory proves its own pi1,1 soundness, is actually an instance of this more general thing. You get genuine well-foundedness. So if you shift your attention slightly from consistency to pi1,1 soundness, you get a genuine well-foundedness claim. And we give a Friedman-style proof of this. So you work in the theory, it's just like before. This time DS says there's a sequence of the kind that we now know doesn't exist. So there's a sequence of RE extensions of ACA0, let's say, such that the X0, the top one, is pi1,1 sound, and for each n, Xn proves the pi1,1 soundness of Xn plus 1. You can prove the consistency of ACA0 plus DS from the inside. I'm not going to give you the proof, but I can actually give you some intuition for why this is happening. Okay, so imagine I'm standing here, and I'm standing in a line. There's a guy standing in front of me. He's looking this way. There's a guy standing in front of him, looking this way. It's an omega sequence, okay? And imagine that each one of us has consistent beliefs and believes that the guy in front of us has consistent beliefs, okay? That's the setup. Here's the issue. I'm looking ahead. The guy in front of me is seeing exactly the same thing I'm seeing, right? We're both just seeing these infinite sequences of guys in front of us. And I think to myself, well, hang on. He must believe the same things I believe. He's saying the same thing that I'm seeing. If his beliefs are consistent, my beliefs are consistent too. So if you have these infinite sequences, I can figure out things about myself that I'm not supposed to be able to figure out, according to Gödel's theorem. Now, to make this argument precise, you need to, you need to tweak some things. If you work in this setting with pi11 soundness, you can make this argument precise. You get no sequence like this. I had the same theorem just on this slide because I want to say a few more words about it. This is a well-foundedness theorem. Like I said, it's literally saying there's no descending sequence of a certain type. So it's a well-foundedness theorem, but it's also an incompleteness theorem. Now, in virtue of the fact that it was a well-foundedness theorem, we were able to prove it just now using the incompleteness theorem. But in virtue of the fact that it's a incompleteness theorem, maybe we can give a Kripke style proof. So maybe we can give a proof of this that doesn't use self-reference or the second incompleteness theorem. Maybe there's a proof of this which just uses considerations of well-foundedness. And it turns out that there is. There is a canonical way of assigning ordinals to theories. Okay? For any theory, there's a canonical ordinal that gets associated with it. This is called the proof-theoretic ordinal of the theory. So this comes out of Gensen-style proof theory. So just to reiterate, there's a canonical way of assigning ordinals to systems. This is the proof-theoretic ordinal of that system. So here's a later theorem, very similar to the statement of the last thing, except slightly more general. There is no sequence T0, T1, T2, and so on of sufficiently strong pi11 sound and sigma11 definable theories, such that for each n, Tn proves the pi11 soundness of Tn plus 1. This is slightly more general because now we're not just talking about RE theories, we're talking about all sigma11 definable theories. So this is again saying there's no descending sequence. How do you prove this? You suppose there is such a sequence. And using the hypotheses of the theorem, you can show that the proof-theoretic ordinal of the nth element of the sequence exceeds the proof-theoretic ordinal of the n plus first element of the sequence. If Tn proves the pi11 soundness of Tn plus 1, its proof-theoretic ordinal has to be bigger than Tn plus 1's proof-theoretic ordinal. That gives a descending sequence of ordinals, and we know we can't find those. So again, this is a Kripke-Kuratowski style proof of an incompleteness theorem. In some sense, I think this theorem is the phenomenon sort of distilled. You have a statement which is simultaneously a well-foundedness statement and an incompleteness statement, which is susceptible to both proofs. It can be proved by using the second incompleteness theorem. It can be proved through this Kripke method of well-foundedness. Okay, so at this point, we started by talking about these puzzles that showed up in Kripke's paper, and now we've gone off in this other direction. Now we've been talking about the incompleteness theorems and well-foundedness. So let's bring it back, okay? Let's bring it back to truth. Here's a recent-ish theorem of Ali Inayat and Fyodor Perkomov. So they showed that this theory, CT minus plus DC, is not conservative over PA. So this is a big result in the truth literature. So CT minus, we have compositional truth axioms, okay? And DC is disjunctive correctness. So this is saying that truth commutes with arbitrarily long disjunctions, right? So it's guaranteeing that it commutes with disjunctions of non-standard length. That's one way of thinking about this. This theory is not conservative over PA. In fact, it proves the consistency of PA. This is a surprising result. Disjunctive correctness, I think before this result was believed to be quite weak. Okay. But they have this non-conservativity result. So this is not a result about incompleteness, or well-foundedness, this is just a result in the truth literature. How do they prove this? One step in the proof involves showing the inconsistency of another theory, DTB. What does DTB stand for? DTB stands for descending Tarski biconditionals, okay? So DTB, what the axioms describe is a uniformly definable descending sequence of truth predicates where you get the Tarski biconditionals at each level. So they show that this system is inconsistent en route to proving this result. How do they do that? Well, they say the proof of this theorem was inspired by the recent James Walsh proof of one of the results that I just mentioned. We proved the inconsistency of DTB by Gödel's second incompleteness theorem. So they don't prove this as you would expect by Yablo's paradox. That's kind of the obvious thing you would expect. No, they show that this theory, DTB, gives you a kind of proof of consistency from the inside, right? So they're using these same ideas to address questions that are sort of just inside the truth literature. So before I conclude, I just want to say there's a circle of ideas here, right? Gödel identified in his original paper that the incompleteness theorems are tightly connected to the semantic paradoxes. And as you deepen your understanding of one, you deepen your understanding of the other. And Kripke put his finger on this. I mean, he deepened our understanding of both of them, of course, but you can see the connection already in his 1975 paper on truth, right? So it's already there. So that's all I have for today, and thank you very much.